All right, how is everyone doing today? Okay, good. Tired, good. All right, does anyone have any questions before we get started? Okay, cool. So today we're going to finish our ether synthesis, or ether reactions actually, and then we're going to roll into discussing synthesis. How do we do those multi-step syntheses? How do we start to think about it in terms of like a puzzle and solving a logic problem? So first, let's finish our ether reactions. So we had said that our nucleophile can attack either the left or the right. And that was the big deal, was that we get this regiochemistry consideration. And so to know if you're going to attack the left or the right, you need to know if you're doing SN1 or SN2, because then you're going to have the substrate considerations if you're doing SN1 or SN2. So SN2, we're picking if we have that strong nucleophile, and you're looking for either a primary or secondary leaving group. So whichever side is attached to the oxygen that only has one carbon attached to it, or two carbons attached to it. For SN1, we're typically going to be looking at the weaker nucleophiles, and really you're going to want it to be either tertiary, or you're going to have a phenolic ether, meaning that you can't, like you have benzene on one side, so you're going to have to go to the other side. So if I look at this reaction, the first step, I have strong acid. If you have strong acid, the first thing you better do is protonate something. Our most basic site is going to be the oxygen. So that oxygen is going to attack the acid and get protonated. So at that point, I am here, and that iodine, or iodide, is a strong nucleophile. So because it's a strong nucleophile, that's telling me that I'm going to do an SN2 reaction. So I want the side that is going to be essentially primary. I want the less sterically encumbered side. So when I consider the two sides of my ether, this side, if this whole thing is the leaving group, that would be considered a primary leaving group, because that carbon is attached to only one other carbon. This side, if this whole thing is the leaving group, then that is going to be a tertiary leaving group, because that carbon is attached to three other carbons. So our iodine, because I want to do SN2, because I have the strong nucleophile, the iodide is going to attack the primary carbon side and kick out the leaving group to give me those products. My 1-iodopropane and my, what would that be? 2-methylpropan 2-ol. So when we were doing that SN2, the nucleophile attacked the less sterically hindered carbon, because SN2 needs to have sterics, is the big thing that we're looking for SN2. All right, when we look at our epoxide rings, here's where a lot of the color coding got messed up. So I tried to make this oxygen always red. So the oxygen of the epoxide, I tried to make it always red. So you might have to change your oxygens to make sure that they're red. The main one that I had to change on mine was this one, to make that one red. And then I tried to make the nucleophilic oxygen always blue. So the nucleophilic oxygen is the one coming from the water. So I had to change those two to be red, or sorry, to be blue, because they were red. Just trying to help keep track of where everything is. So for our epoxide ring openings, we're going to have our, if you have acidic conditions, we're going to do an SN1 type reaction. So the mechanism that we're going to be doing is essentially SN1, but it'll technically all be one step. So it's going to look weird. So it's SN1 type because it's going to have SN1 substrate considerations, but it'll technically be one step because that's going to be faster. The steps are going to happen really quickly, so it technically is one step. So what we're going to see is our epoxide is going to get protonated. And remember, epoxides are just the three-membered rings that are the cyclic ethers. It's specifically the three-membered rings is what we're seeing. So we have that oxygen gets protonated. Now it's a good leaving group. So I can consider having this nucleophile attack either the more substituted side or the less substituted side. And this arrow is incorrect. So it is the oxygen is coming in and it's going to attack the more substituted side because that's what SN1 does. So because it's a weak nucleophile and it's an SN1 type reaction, we're going to attack the more substituted side. So I have to open up the ring on the left-hand side. So it's the left bond that pops open. So then I see that I now have the blue oxygen, the nucleophilic oxygen is attached to the left carbon. On the right-hand side, I still have that oxygen attached, right? So if I were to number these carbons, like 1, 2, 3, this is 1, 2, 3. I only disconnected the red oxygen from carbon 2. It remains attached to carbon 3, right? It's just folding open. It's not totally detaching, it's just breaking one side to kind of fold open. And then the last step is just that we need to deprotonate in order to get it neutral. So you just use another molecule of water, will get you to a neutral product, and you get the diol. So the question of, well, why did we attack the more substituted side? And it comes down to whichever bond is longer. So when we're in acidic conditions, and we have this protonated epoxide, you can imagine getting this, either breaking this bond and you get this partial positive on that carbon, or if I imagine breaking, the left-hand side, then I would get a partial positive, or I'm getting a positive carbocation on the left. So you never actually form a true carbocation. We're just thinking about which side is more electrophilic. So if I were to make a carbocation on this side, it would become a primary, so that would be less favorable. Whereas this side, it would become a secondary, that would be more favorable. So because of the fact that that is going to make it more favorable, that is going to be one way to think about how that is the more electrophilic side. The reality of it is because you don't actually make a carbocation, so it's just using the carbocation mentality to try to rationalize it. But what's actually happening is that carbon is an electron donating group. So that carbon is pushing electron density in. So when it pushes electron density in on the left-hand side, it's going to push that oxygen out a little bit. What that's doing is that's lengthening that carbon-oxygen bond. So this bond is longer on the left-hand side because I have that carbon substituent pushing it in, lengthening that bond, and that makes it weaker. The longer bonds are weaker, the stronger bonds are shorter. So the longer bond is now weaker, that's the one that more readily breaks. So that's why it's actually going to be that bond that is the one that breaks, and our nucleophile attacks the more substituted side because that becomes the more electrophilic carbon because that is the weaker bond, making it essentially the better leaving group. Cool. All right. When we're doing an SN2 reaction, so we're going to be in basic conditions. So we're going to have the strong nucleophile, that O-. Then we're going to do SN2. And really, we don't even have to call it SN2 type. It actually truly just is SN2. It looks a little weird because it's an epoxide, but you're just nucleophile attacks, and it pops open the ring. So it's going to be this or your nucleophile is going to attack the epoxide on the less substituted side. So SN2, you want less sterically encumbered. So it's going to go to whatever side has less sterics to just pop open that ring. And then you just have to do a protonation in order to get it neutral. So you just have whatever your solvent is, most likely is that same thing. So this would just be solvent. Is then going to just protonate your alcohol. So what the reduced selectivity looks like is if you have basic conditions, meaning you have O minuses or whatever's your strong base, then you're doing SN2. And your nucleophile ends up on the less substituted side. You keep the oxygen of the epoxide attached to one of the carbons. And for the SN2, your oxygen of the epoxide is on the more substituted side because you're going to have the nucleophile come in and open the ring on the left-hand side if you're doing SN2. So you get your nucleophile on the left for this molecule. If you are in acidic conditions, then you're going to do that SN1 type. So if you have a strong acid with your epoxide, then you're probably going to be doing a SN1 type reaction, meaning that your nucleophile is going to be attached to the more substituted side. So now your nucleophile is on the right-hand side, and your oxygen of the epoxide is on the left. Right? It's just looking at which bond we attach to. So if I number these, 1, 2, 3, 4, this is 1, 2, 3, 4, or 1, 2, 3, 4. So you're either having your nucleophile attached to carbon 2 of your epoxide, or your nucleophile is attached to carbon 1 of the epoxide. Cool. Any questions about epoxide reactivity? One way that a student once told me that they memorized it, which I thought was a pretty good trick, was that they do A1B2. So A meaning acid, they did SN1. In base, they did SN2. So it was like the letter A comes first, the letter B comes second. So A1, B2 helped them remember which reaction they were doing. I thought that was pretty clever. All right, cool. Let's do synthesis. All right, so we've learned a lot of different reactions at this point. So it's important to kind of figure out, all right, well, when do I use each one? And that's our planning a synthesis, to know when you're going to do each of your reactions. So these are like logic problems, they're the critical thinking, they're actually why I like organic chemistry. I think it's kind of fun, but it is what makes it more challenging is that there's going to be many correct answers. So there's more than one right answer. And so when you're doing these syntheses problems, it's going to be important to recognize that if you look at the answer key and the answer key lists one answer, that doesn't mean you are wrong. It just might mean that you're not the answer that I thought of. So if you're ever unsure and you can't prove to yourself that you know you're right, I want you to ask. I want you to go to a TA. I want you to ask me. I want you to ask your peers and be like, hey, do you think that this would actually work? because you might still have a correct answer, right? There's more than one correct way to make a molecule. There's usually one way that's more efficient, where you have fewer steps, or maybe one way is more selective, so that it's going to be higher yielding. But that doesn't mean your way is wrong. It just maybe it's not the best way, or maybe it's equally as good. There are many right answers. So we've already seen this, but when you're thinking through the forward reaction, you want to identify your nucleophile and your electrophile. Identify what has electrons, what doesn't. Ask yourself, are we going to be doing acid-base, or are we going to be doing substitution? If you're doing true acid-base, meaning you have a strong acid, protonate something. You're going to do that first. Acid-base chemistry is very fast. If it's a better base, then you're probably doing elimination. And you don't have a strong acid, then you're probably doing elimination. All right, so figure out what has electrons, what doesn't, and then draw an arrow from your nucleophile to your electrophile, from the nucleophilic atom to the electrophilic atom. Go from what has electrons to what doesn't. Then check, did I violate the atom's octet? Did I violate that electrophilic atom's octet? If yes, then I need to draw a second arrow going away from it. If no, then cool, just keep going. Then you're just gonna draw your product. I'd make sure you know what bonds you've broken, which bonds you've made. Number your carbons, number your atoms to make sure that you're not adding or losing any carbons. And consider that stereochemistry. Make sure that you know, do I need it to be a wedge or a dash, or should it be a line? Make sure you're considering that stereochemistry. So that's our forward synthesis. That's what we've kind of already been doing. That's the predict the product. Retrosynthesis is asking the question, cool, how do I make that? I'm working backwards. So you're looking at a target. You're saying, I want this. So then what do I need in order to make it, right? So that's my product is the target. And then my starting materials, your reactants, your reagents, those are what you need in order to make that. We have our retrosynthesis arrow, which is like the equal sign that became an arrow. So it's that open arrow. It always points to the starting material for your retrosynthesis arrow. So when we think about the different ways of making our molecules, or the ways of approaching these syntheses, if you just have your starting material and your reagent, and you're just going forward, then that is forward thinking. That's usually the easiest synthesis problem. And that builds up to our hardest as we go down. So the easiest, stop moving. Easiest being, I know what elements I'm starting with, so what does that do? That's usually the easiest. A little bit harder is going to be, all right, let's fill in the gap. I recognize my starting materials and my products, and I gotta say, all right, what reagent will make that? So then that's a little bit harder where you're trying to fill in the gap, because you can either work forward or backwards, right? So you can either think of, all right, what are all the things I know to do with that starting material, or what are all the ways I know how to make that product? So you can think of it in either direction to try to identify what is my reagent. If you have a product and a reagent, and you're now asked to think of the starting material, this is harder, but it's because you have to think backwards, but you get a little bit of help because now you're told, all right, well, which reaction are we doing? And the main thing to keep track of is what elements is that going to impact within my product, right? So that's trying to say, all right, so what elements did I have to start with because they didn't come from the reagent? So it's thinking backwards with a little bit of help. The absolute hardest is where you're trying to think backwards with no help. So this is, you just need to come up with a total synthesis on your own, and you have to think of what are some reasonable starting materials, what are the reasonable reagents, and so then this is the absolute hardest thing to do. The way that these questions are phrased, because there's so many opportunities, like there's so many answers that could go there, is that normally these questions are gonna say, all right, you have to start with reagents that have fewer than 3 carbons or something. So that way you know what your building blocks have to look like. You'd have to be told some sort of hint. or you'd be given like a molecular formula or something to tell you where you're starting from. You have to have some hint. Otherwise, the answers are like so many. Like you could have so many answers and still be right. So hints to keep track of when you're trying to think of syntheses, when you have like multiple blanks and you're trying to fill in these boxes. Most of our reactions are going to occur at or next to our functional groups. So think about where you can change having a functional group. The elements gained must appear in either your starting material or your reagents. We're not going to be alchemists. We're not going to create it out of nothing. You had to start with them somewhere. Then most of our general types of reactions are either those functional group interconversions. So how do I go from an alkyl halide to an alcohol? Or where we're building carbon-carbon bonds. Those are usually harder to spot because it doesn't look like there's readily a functional group available if you're trying to build those non-polar bonds. So usually if you're building those carbon-carbon bonds or carbon-hydrogen bond, you got to think, all right, that means I'm doing one of my like reductants or something. I'm using a Grignard, the organolithium, lithium aluminum hydride, or sodium borohydride, right? That's what's giving you those carbon-carbon or carbon-hydrogen bonds. So when you're trying to make a synthesis, try to do the shortest synthesis possible. It's usually easiest to break molecules apart in the middle and then kind of build up the pieces, as opposed to like trying to work left to right across a molecule. It's usually easiest if you kind of like try to break it in half and then imagine building up each piece. Disconnect at your polar bonds or wherever you see any key carbon-carbon bonds where you're recognizing like, ooh, that could potentially be a Grignard adding in there. So try to break it in the middle, we said that. Look for any branch points or rings and use symmetry to your advantage. And the better solution, so there are multiple right answers, but the better answers are going to be the ones that are considering that regioselectivity and the stereoselectivity. So that's going to say, do you get full credit or partial credit? Did you make it regioselective, or did you not pick the right base, kind of thing? Like, did you use a bulky base or a non-bulky base? That is going to be the difference in what you're doing. And make sure you keep track of your carbons. It's always so frustrating when you lose points because you didn't count your carbons. All right. So the general process for a retrosynthesis is first you're going to analyze. Ask yourself what is different. Recognize what are the functional groups that are in the target molecule, and when in doubt, make a chemical inventory. So the chemical inventory is where you're actually just saying, okay, I can't even see what is different just by looking at it initially. So I'm going to count how many of each element do I have. So I'm going to do my starting material and my product. And I'm going to say, all right, what elements do I have? So I have carbon, hydrogen, bromine. I have carbon, hydrogen, oxygen. And I have, I don't know, whatever the numbers are. I can't think of reasonable numbers. That's also not bromine. That's bromine. So you just look at, okay, just a pure chemical inventory. What elements did I start with? What elements did I end with? What is the difference? That's what we're trying to figure out, because that's going to help us know what reagents we need. The next step is, once you know what you have to do, try to think of how I can do that. Think of, how do I know how to make that? So think of reasonable disconnections, and you want to look at reliable reactions. So this is where reaction roadmaps can help. So on Friday, I had asked you to create a reaction roadmap, filling out those problems for, or the reaction roadmaps for recitation. It's essentially looking at things like this, where you're given a target, and it's, what are all the ways I know how to make alcohols? All right, well, I know how to make an alcohol by doing my ester hydrolysis, right? I know how to make an alcohol from the ester hydrolysis. I know how to make an alcohol from my substitution reactions. So from doing SN2 or SN1. I can make an alcohol by reducing a ketone with sodium borohydride, doing that reduction, or potentially lithium aluminum hydride. Or we could have added a Grignard in, and that was adding in the carbons, but also giving us the alcohol product. So doing a different type of reduction, and it could also be the organolithium, right? So then these are our products. It's important to note right here that this is a common flaw that happens on our reaction roadmaps is one, sometimes they omit acid workups altogether, or two, they might list it above and below the arrow, but they forget the numbers. So if you're using someone else's reaction roadmap, make sure you pay attention to the fact that we're always going to count the acid workup as a separate step. I want you to tell me that you know that you have to add that hydrogen in order to get the hydrogen on oxygen. So we will always count the acid workup as a separate step. It's going to be that HCl and H2O as our acid workup. And sometimes you'll see it just say dilute to really reinforce acid workup. So dilute acid to really help state that like we're only protonating it, or you could write like one equivalent or something. So then these are all the ways we know how to make alcohols. This way we haven't talked about yet, but we will. This is our addition reaction. So we will eventually build in even more so you can complete the reaction roadmap as you go, right? So the benefit of these roadmaps is now it's summarized what are all the ways I know how to make this. So then when you're trying to do your synthesis, you have to think, all right, well, what is my starting material? Am I starting from a carbonyl? Okay, then I'm going to be doing one of my reductions. If I have a carbonyl as my starting material, and then I just need to pay attention to, do I want hydrogen or do I want carbon? What am I trying to add in? Then what if you have an alkyl halide? Cool, then I need to do substitution. What if I have an ester? Then I'm doing ester hydrolysis. It helps you recognize these functional group transformations. What was the functional group you start with, and that helps you know where you have to end. Reaction roadmaps also sometimes have these two-way streets where it's saying, if I want to go from the ketone to the alcohol, cool, add sodium borohydride. But if I want to go from the alcohol to the ketone, then I'm going to add PCC or Jones. Right? So it's looking at, if you're going this way, you use this reagent. If you're going that way, you use that reagent. So this is just another way of having essentially your reaction notebook, right? So either you can have a page for each of these, all written out, because these are all the, well, that's acid workup, but for each of these, because these are all the reactions we've talked about so far. So you can either have a page for each of them, or you can make it a list and have the running list of all the reactions that we've done, or I guess, and you could do all of them if you want, or you could have this like circular map where it's your targets in the middle and then everything you're doing to build into it is around the outside, right? So in recitation, or before you get to recitation actually, please do the reaction roadmap to complete that. It'll, one, make sure that you're using recitation time more efficiently, so that way you know, you can do more synthesis problems and actually practice the complicated problems, how to use the reaction roadmap. But if you don't, they will give you the answer key beforehand. So it's better if you do it yourself though. That's active studying. If you do it yourself and then check your work, as opposed to just relying on them to give you the answer. Okay, that's mine, anyway. So this is how you'll know what are my reactions I know to get to that desired product. If you're like, I'm stuck, I'm pretty sure there's some reaction, but I can't remember what it was, then you can use synthons. Synthons are not real, but they can be really helpful. So it's just what we're doing for a synthon is just, let's break the bond based on the normal polarity of the bond and see if I can make that real. How can I turn that into a reasonable thing? So what a synthon looks like would be something like this, where if I'm looking at, I find my polar bond. That's the thing that I want to make. So I'm going to say, all right, the polarity, the natural polarity of the bond is such where the oxygen's more electronegative than the carbon. So the oxygen's pulling electron density away. So what if I just break that bond, imagining that I'm like, cool, I'm just going to give those electrons to the more electronegative atom, right? To try to think of, well, what's a reasonable place that I could have started? Is that would have made my oxygen the nucleophile, the carbon the electrophile. So it follows the inherent polarity, inherent reactivity of our molecules. So then what that does is it gives me that carbocation and O minus. So these are the synthons, because these aren't real things to start with, right? It's not saying that like, this is your starting material. We're not gonna have a primary carbocation, that's not a real thing, but it can help us think of, all right, what is a reasonable place that I could have started? Anytime you see carbon with a positive charge as your synthon, think leaving group. If I need electrophilic carbon, I'm gonna put a leaving group on it and that does the reaction. So what I'm actually gonna do is be like, all right, well then for this thing, I just need a leaving group there and that'll make that. That equals essentially that. Let's do approximately equal to. Just having a leaving group on that carbon, that makes that electrophilic. And then if I'm trying to think of, all right, how do I make the hydroxide nucleophilic? Well, the benefit is hydroxide is kind of a thing, right? So the only way I need to make it real is to give it a counter ion. So then I'm just gonna pick whatever's my favorite counter ion to maintain the O minus. So how about sodium hydroxide or something? And because I wouldn't leave it as generic leaving group, I'd actually have to pick an element. What's your favorite leaving group? Iodine, cool. This is where I'm saying like there are many right answers. So then you're gonna say, all right, cool. So I know how to take my iodoethane and sodium hydroxide to make that ethanol, right? So that's that general process. So the synthons are just, let's just break the polar bond and give the electrons to the more electronegative atom, and then try to think of how can I make that a real thing. If I want it to be an ion, give it a metal. If I want it to be electrophilic and it's carbon, give it a leaving group. And so then that's the general process that we're gonna go through. If it's one step and it's just that easy of like, cool, these are the things I'm starting with, we're done. Most of our syntheses will not be that straightforward. Most of them will be multi-step, meaning they have more than one step. So then the question becomes, which step must be first? So what you want to do is write out the reagents and the conditions, and then just essentially guess and check. So if you're like, I'm gonna do this step first, determine if the desired product is the actual product form. If it's not, change the steps. So if you're like, all right, I have this alcohol, and I do this first, and that brings me to my intermediate. And then I do B, and I get a different product. Then I'm like, cool, I'm just gonna switch the steps then. I'll do B first, get my different intermediate, and then do A, and now I get my desired product. So this is what I mean by like guess and check. Just try to do one of them first. The more synthesis problems you practice, the more you'll start to identify, okay, acid workups always have to come after the other thing, like after the Grignard addition or whatever. So then you know that that's got to be towards the end. Or you'll recognize like, hey, I want this carbon bond here, so I'm gonna have to do that earlier on. Well, that other site is electrophilic. The more you practice, the easier you'll be able to start to identify like, oh, B had to come before A for this to happen. But when in doubt, guess and check. Just pick one, see what it does, and then see if you do the other step, does it give you your desired product or not? If not, just switch them up and then check yourself again. All right, so we're gonna do that process here. So we're gonna propose a synthesis to get from that bromine, or no, sorry, from the alcohol to the bromine. So remember that when you have your retrosynthesis arrows, your product is at the beginning, your starting material is at the end. So another way of writing this, the way that I usually will write it on exams, is that I will give you either, I'll write multiple arrows to show that there are multiple steps, and then I typically do like a question mark, or I'll give you a big blank arrow, and then I'll just expect you to write your steps above and below the arrow, right? All right, so step one, we're gonna say what's different. So what's different? What about the leaving group? Yeah. Yeah. Yeah, so we have OH as our leaving group. So we need to lose an OH and we need to gain a bromine. So what's different? I have to gain a bromine and I have to lose an OH because the OH is the leaving group. So that's what's different. So if I'm doing the chemical inventory, if you're ever, this is a pretty straightforward example, there will be times where you're like, I don't even know where to start. Or it'll be really complex looking and anxiety is kicking in and you're like, I don't know what to do with that. Do the chemical inventory. Just at the bare minimum, just be like, all right, well, what elements do I have? Fall back on that. Once you start that process, that usually gets over that initial anxiety to be like, okay, let me just try to like, I'm doing something, and then usually your brain will start to kick back in. So if we're just doing a generic chemical inventory, just to practice that, what are the elements that I have in my starting material? I have oxygen and hydrogen, and what else? And carbon. Cool. In my product, what elements do I have? Carbon, hydrogen, and bromine. Just to keep it kind of similar, I'm going to keep them in the same order. So I'm going to do carbons next to each other, hydrogens next to each other, and then the heteroatoms next to each other. But it doesn't actually matter. You just got to compare. So when I look at my starting material, all right, how many oxygens do I have? 1. How many hydrogens do I have? So 3 plus 2 plus 2 plus 1 is 8. Yes. All right. How many carbons do I have? 3. All right. There's 1, 2, 3 carbons. All right. So then I'm going to look at my products. So for the product, how many bromines do you have? 1. How many hydrogens do you have? There's 3, 2, 2, so there's 7. How many carbons do you have? 3. So what this helps you see is that you are losing that one OH and you are gaining that one bromine, right? So by seeing the functional groups, that's way faster, but doing the chemical inventory got us to the same point. So that's that. If you're like, this thing is so weird looking, I don't even know what to do the chemical inventory, and that'll tell you which elements you need to gain and which ones you need to lose, right? Okay. So now I have to think of, all right, what are all the ways that I can make that? So if we do the synthon process, I'm going to say, all right, I have 2 options. So even if you're forgetting that you have to give the more electronegative atom the electrons, that's the typical way of doing it, you technically can consider either way. So there are 2 options you can consider. We'll do the blue route or the red route. So our blue route is going to give us the 3 carbons with the positive charge and bromine with a negative charge. The red route is going to give us the 3 carbons with a negative charge and the bromine with a positive charge. So if you want to then think about like, okay, which way do I want to break this? Which, what original nucleophile and electrophile combo makes sense? We want to try to think about, okay, well, which one of these looks more normal? Use your chemical intuition to be like, which one have I seen before? The thing that jumps out first at me is I don't know how to do electrophilic bromine yet. So I don't know how to do that. So if I don't know how to do that, I'm not going to try it, right? I'm going to try the easier thing first. So what is that? Is that Occam's razor? Like the simplest solution is probably the correct one? I think that's Occam. Oh, whatever. So whatever is the simplest solution is probably the correct one. So I'm not going to do that one. I'm going to do the one that's easier, where like I know bromide, like that's a thing. I know that I can have that carbon with a positive charge if I make that a leaving group, right? So I know I can do these reactions. So then I'm going to say, okay, how do I make that real? So how do I turn this set of synthons into real reagents? So if I'm trying to make that alcohol, because I have to start from an alcohol, I know I have to start there, then the question becomes, all right, I need to eventually turn that into something with a leaving group, right? That's turning this thing into that thing. So it's somehow I have to make that a leaving group. I have extra information. I was given a hint because I was told that my starting material had to be an alcohol. So I might be able to start directly from the alcohol and have this be an intermediate, or I might need to come up with an extra reagent in order to turn my alcohol into a good leaving group. Plus, I'm going to have that bromide, which just is a thing, right? So let's consider what are all the ways that we know how to do this. So I can turn, like if I just want to make bromide real, I'm just going to say like sodium bromide. Like if I just want ionic bromine, let's consider sodium bromide as one option. It might not be right, it doesn't matter. We're just trying to think of like what are all the possible ways I can get that element. So what's another way that I could get that bromine to be added in? What's another reasonable reagent? HBr, love it. That's another reasonable way of adding in that element. Can we think of, oops, I don't know why I changed from letters to numbers. Can I think of another reasonable reagent that added bromine in? Talked about it last class. So there's PBr3 is another option. Was another one that we could have done. So now we want to try to consider what are all the ways that I can make this real? Like how do I put this together? So let's actually take this space up here. Because I don't think yeah, that's a different synthesis. Okay, so if I just consider, let's do option A. Let's say if I just start with that alcohol and I try to add sodium bromide, does that work? Do I get that desired product? So I see some head shaking no. So you're absolutely correct. That does not work. So why doesn't it work? Yeah, the alcohol isn't a good leaving group. So you're trying to do SN2, but what you're doing is you're creating something that is a good leaving group and a really reactive reagent. So we said that that is only going to go backwards, so that did not work. All right, so that takes away the sodium bromide. We're like, no. That'll only be okay if you do it in 2 steps. So to think of like, okay, well, maybe I'm really glued on sodium bromide. Maybe I can't think of any other reagent than sodium bromide. So then an alternative, so we'll say A.2. So like I'm really stuck on sodium bromide. What could I do to that alcohol in order to make it a better leaving group? So we could protonate it, but we can't do that with sodium bromide. So that would be that same protonating it. How about our sulfonates using that tosyl chloride, trifle chloride? That would let you do your SN2. That would work, but it's 2 steps, but that would work. So that's turning your alcohol into a good leaving group first. That does give you your desired product. So if we don't care about step count, then beautiful. That works absolutely. That's a reasonable synthesis. Let's consider that protonation that we were just talking about. All right, what if we're going to just consider like sodium bromide didn't work for us, so let's look at HBr. Let's consider that alternative. So if I'm like, all right, I have that plus HBr, does that work? What does that give me? Yeah, that works, right? Because that is that protonation that we were talking about. So we can protonate the alcohol, you get the good leaving group in solution, you make that oxonium ion, so that I'm making the good leaving group all in one step to then have, or all in one reaction step. So I'm protonating and then the nucleophile can come in. So yeah, that's doing acid base, then SN2. That works, that will give you your bromine. Something we have to watch out for though, so that works, but it risks SN1. With different substrates. So for this substrate, yes, it absolutely works, it's beautiful. But I'm gonna keep in mind that like, if there's the chance of having carbocation rearrangements, if there's like a secondary alcohol or a tertiary alcohol, SN1 might outcompete. So in this case, I'm totally valid. That works because it's primary, we're good. But it runs the risk for other substrates. So it might not always be a reasonable reagent. But for our substrate right now, because it's primary, it is okay. And then we're going to be like, all right, well, let's consider C. Option C was the alcohol using PBr3. And that also made that bromine, and that works because this is always SN2. So if you're forced to pick one step, that is maybe you have a secondary substrate that could have rearrangement, then the only correct answer would be PBr3. But here, you actually have 3 correct answers because I didn't limit you in the number of reagents or number of steps. And so you have multiple correct answers. So all 3 of these are correct. So the last part that I will always ask you to do is then to make it a complete synthesis. So that means that I won't always do this. I will tell you whether or not you need to. But if you get in the habit of doing it every time, then it'll be really easy. So I will ask you to include reasonable reaction conditions, including solvent and temperature when necessary. So if I need to include solvent and temperature, I didn't do that here, right? All I did was include the key reagent that I wanted. So if I need to include solvents, let's think of reasonable solvents. So if I'm wanting to do SN2, what kind of solvent do I most likely want? Some aprotic solvent. And so then you just pick whatever is your favorite aprotic solvent. Usually when you have halogens, you will typically pick a halogenated solvent. It doesn't matter. But if you're doing, let's say you do PBr3, because you think, all right, this is the reagent I always use to turn an alcohol into a halogen or thionyl chloride. So it actually, I guess we should have had a part D of SOBr2, which would also work. Then the solvent, I would just do like DCM or something. So that's dichloromethane, CH2Cl2. Or you could do carbon tetrachloride, or you could do acetone, or you could do DMSO. You could do whatever is your favorite aprotic solvent. If you're doing PBr3, then I don't have to worry about the temperature because I don't have to worry about elimination, right? It's just going to be substitution. So I can leave it as room temperature and not have to think about it. So that's the added benefit there. Actually for all of these, because bromine's never going to be a base, so I don't have to worry about that for any of these. But that might be a consideration we want to make. Okay, so this is what I mean by like there can be many correct answers. So you may, on a practice test or a practice problem, you might see that only PBr3 is written, but maybe you wrote HBr. One, if you can prove to yourself HBr is valid, if you can draw the mechanism and be like, yeah, I know, yeah, those arrows work, I know this works, then that's the best because you can't ask me on an exam like, hey, is this right? Would this also work? Because I'm going to tell you, I'm sorry, I can't answer that question. But before the exam, you can also then ask me and say, hey, would HBr also work here? And I will tell you, yes, that is absolutely a reasonable reagent. That is another correct answer. Okay. So that's the challenge with synthesis, is that you always need to like double check the answers, and the answer key might not be every possibility, because what I absolutely love about these problems is that your creativity gets to show. The way you think about it, you might have come up with a more creative solution, and that doesn't mean it's wrong. It's just different, and it can still be absolutely correct. So next class, because I really want to get to these types of problems, next class we'll do these two synthesis problems, so we won't start chapter 12 yet. We'll finish this out. All right. Have a wonderful day.